Okay, this is actually video 3 in a series of launching a spacecraft from an asteroid. And so I have a picture of an asteroid because I'm using a presentation. And in the previous 2 videos, I used the work energy principle, and now I'm going to use the momentum principle. So let's get started. This is a solution before. I remade this video and I'll link to it down below. But the main idea is to use this spring to launch a spacecraft from an asteroid, and we want it to end up at a final speed that's really far away of, let's say, 12 meters per second, and I want to find the spring constant of that spring in order to launch it. The nice thing about work energy here is that it doesn't matter that the force has changed. It doesn't matter that the spring force changed. It doesn't matter that I don't know how long it's going to take, because work energy doesn't depend on that. Work energy depends on just a change in position. And so here I say the system was the spacecraft plus asteroid plus a spring, and the total work was 0. So the change in energy has to be 0, and then you can solve for what you need. And I'm not going to go over that solution. There's a video, like I said. I actually have 2 videos on that. Instead, I want to do this with the numerical calculation, because that's what a lot of students like. Or I'm sorry, the momentum principle is what they like, and we're going to have to do that with the numerical calculation. So I do have the solution down here, the spring constant of 1.25 times 10 to the 5th newtons per meter. We'll use that later. Okay, so how do we do this with momentum principle? So I'm going to explain the process of a numerical calculation using the Euler-Kromer method. There are other methods out there, but this is the one that works fairly well, and it's the simplest to understand. So imagine I have some object here. It's at position 1, and it's going to follow some path that I don't know what that path is, but I do know that after some short time interval, delta t, it's going to be at a new location, position 2. And then a little bit later, it'll be at another location. So I can just break this motion, and instead of finding out where it is at the end, break it into a small step. Now, there should be some force acting on this object. I'll call it F net. And it is moving with some initial momentum, P1, where momentum is mass times velocity in this particular case. What I can do, since this is a situation where the force can change going from 1 to 2, so it could be quite difficult. However, if my time interval is short enough, then I can assume that the net force is constant and make the problem easier, going from just position 1 to 2. And then I'd have to do going from position 2 to 3, and 3 to 4, and so forth. So instead of one hard problem, I have a whole bunch of simpler problems. But here's at position 2, it has some force and some new momentum P2. So the key is, can I find just that? I just want to just go from P1 to P2. And then after that, I can go to the next one and find the force over there and P3 and so forth. So that's the goal here. So how do we do that? We're going to start with the momentum principle. The momentum principle says that the net force on an object, if that force is constant, is the change in momentum divided by the change in time. If it's not constant, I'd have to write that as derivative. Take the limit as delta t goes to 0, and you get a derivative. So since this is a constant force, I can write it this way, and I can write the change in momentum as P2 minus P1. That's what change means. Now, if I multiply both sides by delta t, I get P2 minus P1 equals F net times delta t. And finally, I'm going to add the vector P1 to both sides of the equation, and I get this. This is super important. This is the momentum update formula. It says if I know the momentum at P1 and I assume the force is constant, I take that force, multiply it by the length of my time interval, add it to my initial momentum, and I get my final momentum. Okay, but now where is the object? Now we can do the same thing by using the definition of average velocity. Average velocity is the momentum divided by the mass. It's just straight from the definition of momentum. And it's also the change in position divided by the change in time. And here I'm using r as the position. So I can again write delta r as r2 minus r1, multiply both sides by delta t, and add r1, and I get the position update formula. This says I'm going to take that momentum, multiply it by delta t, divide by the mass, add it to my old position, and I get my new one. And these are all vectors, so it's actually moving in 3D space. That's the plan. Okay, now we do have some issues here, and let's first think about the forces that we need to calculate. So here's an illustration of my asteroid launching my spacecraft. So there's my compressed spring. The red thing is my spacecraft. The gray thing is the asteroid. I want to find the force the spring exerts on the spacecraft because it's not constant. So the first thing I'm going to define is this vector L. L is the length of the vector of the spring. So it's from the beginning of the spring to the end of the spring. I also need the distance L0. This is the unstretched length of the spring, because springs, the more you compress them, the greater the force. So it's a non-constant force, and I can calculate that force using this. I'm going to also need this L hat. L hat is a unit vector in the direction of the vector. So with that, I get the following expression for the force due to a spring. Negative k, where k is a spring constant, the difference in length of the actual length of the spring times subtracting the unstretched length. And then in order to make the whole thing a vector again, I have to multiply by that unit vector L hat. So in this case, notice that L is shorter than L0. And so that's going to be a negative number inside the parentheses. But then I have another negative outside, so this is going to be a force in the same direction as L hat, which is what I want. I wanted to push it away. Now we have another special condition here, because I don't want the spring to, I want it to be a launching spring, so I don't want it attached to the spacecraft. So I'm going to have to say, if the length of L is greater than the unstretched length, then there's no force. And so I just have to turn off the force. Otherwise, you'll pull it back and it'll just oscillate back and forth. And I don't want that. Okay, so that's how I'm going to calculate the force due to a spring. Well, what about the gravitational force? Well, here's a little bit later. The spacecraft is further away from the asteroid. There is a gravitational force. The first thing I need to do is find this vector from the center of the asteroid to the center of the spacecraft, and we're going to call that R. And since neither the asteroid nor the spacecraft have to be at the origin, I actually need the relative positions of the spacecraft and the satellite, and the asteroid, I'm sorry. So the vector R is going to be the vector position of the spacecraft minus the vector position of the asteroid, and that will give me the vector R. And then from that, I can calculate the gravitational force with the universal law of gravity, which says that the gravitational force is negative g, where g is a constant, mass of the asteroid, mass of the satellite, divided by the distance between them squared. That's the magnitude of r squared. And then I need that r hat there too, because again, I need a vector force, because I need to use the vector force to update the vector momentum. So that r hat is just a vector pointing in the direction of r. There is one other thing. So this is the force on the spacecraft. However, the force the asteroid exerts on the spacecraft is the opposite of the force the spacecraft exerts on the asteroid, and for both the spring and for the gravitational force. If the mass of the asteroid is very large, that force is not going to make the velocity change very much of the asteroid. But if they're closer in size, which we're going to do later, then it does matter. Okay, so we may have to calculate both the force on the spacecraft and the asteroid and update the momentum of the spacecraft and the asteroid. Okay, so here's the plan. Number one, calculate the net force. So that's the force due to the spring and the gravitational force. And maybe the spring force is 0. I don't know. Okay, after that, I'm going to update the momentum. Now, here I just calculated the force, which depends on the position, right? So it does change, but I calculated it. I'm going to assume it's constant. I'm going to use that to update the momentum. Next, I'm going to update the position. Now here's a little trick. Notice that it says P2 delta T over M. So I'm going to use the momentum I just calculated, the momentum at the end of the time interval, to update the position. That's not the average momentum. It's the momentum at the end. So it turns out that if delta t is small enough, that doesn't really matter, and this works really well. So I'm going to do it that way. Finally, I need to update time, because I need to move to the next time interval, so I want to update the time. I may not need that time, but I'm going to do it anyway. After that, you just go and do the whole thing again. You just repeat this until you get what you want, which is really far away. Okay, so we have some questions before we start programming. Number one, how far is far, right? How far? I want it to be really far away. If in the work energy principle, I just set R is so great that the final potential is 0. But how do I do that here? So we're going to need to think about that. And I'm going to start programming it, and then we'll start figuring that out. What about the time step? This one is a little tricky, because if you want it to move far away, you would want either, you want larger time steps, right? But if you have large time steps at the beginning, it's going to mess everything up. So we'll play with that. I might have to do a changing time step, but let's just see. I don't know. I haven't written the program yet. I'm doing this on the fly. Okay. So I can find the final velocity at the end of a time interval, but then, and I can model this even if I get it really far away and I can see it doesn't change. But then how do I find the spring constant, right? I can't, because I have to use that spring constant to calculate the force. So there's kind of a problem there. Let's just get it to work. I'm just going to use the spring constant that we had before and just get it to work. And then we can go back and kind of work backwards and see if we can figure out what spring constant would work. Okay, so we're going to go over to Python. I already have some stuff jumped in there. I'm going to use a visual representation of the objects, but that's not super important. Okay, I'll see you there. Okay, so I've got a little jump start here. This is trinket.io. It's a way to code Python online. I'm using if you go up here and you want to do a new one, actually you can't see it all the way, but if I click this, new trinket, you always want to do glow script because it has the visual stuff in there. And you can see here that I've already put in some of my constants. That's fine. So let's just start building the things. And the first thing I'm going to do is make my asteroid. So let's just call that, we could call it Bennu. Was it 2 N's or 1? I'm just going to call it that. It's a type of object sphere. I'm going to put it at the origin, although it doesn't really matter. And I'm going to give it a radius of RA. That's it. So if I click run, there's my asteroid. I can rotate around, I can zoom in and out. Okay. Now let's put in the mass. I'm going to do this Bennu.m equals MA. Bennu.p equals MA times vector 0, 0, 0. And yeah, I don't really need this at first. I should probably not even put that in there right now. Now let's make the spacecraft. Do you want it a box or another sphere? I think I'm going to make it a box. So let's call it spacecraft equals box. Now the position is going to be off the surface of the asteroid. So let's put this position at a little bit higher, a little bit above it. So it's going to be Bennu.pos, that's the starting location, plus the vector. I'm going to put it in the x direction. So vector RA plus 1, 0, 0. And then the size is going to be vector. Okay, now I can make this a reasonable size, like 10 by 10 by 10. Let's make it a box. 10 by 10 by 10. Oh, that's not right. And then I'll give it a color. Color equals color.yellow. That should show up nice. And then make trail, so leave a trail behind it when it moves, equals true. Okay, but now if I run that, I don't know why it's so slow. There's the box. I don't know if you can see that. You see that? There it is. And that's, even that's a big spacecraft, 10 meters. It's just not big enough. Okay, it's not big enough to see. So I'm going to make it look bigger, 100 by 100 by 100, but I'm going to keep the mass the same. Okay, can you see it now? Yeah, that's good. Still looks good. Okay, I'm happy. Now we can go down here and do spacecraft. Spacecraft.m equals ms. Spacecraft.p equals ms times vector 0, 0, 0. So this is important, right? Because I'm going to update the momentum. So I need to have a starting momentum. Even if that starting momentum is 0, there has to be a value. Okay, now the next thing I need is, I have my spring constant, but I have my stretch, S, but I don't have my unstretched length. So if I stretch it 1.6 meters, let's say that the unstretched length is going to be, L0 is going to be, it's got to be at least 1.6 meters. Let's say 3 meters. Also, you'll notice there's no units in my numbers because this is a numerical calculation. The computer is calculating the values based on the numbers. I can't put the units in there. Okay, I need G. I got G up there. I need T equals 0 and dt equals 0.01. I think that might be not super great, but that's fine. Okay, I think that's good. Let's now just make a loop. Let's say while t is less than 10. Just do it for 10 seconds. It's not going to be good enough, but let's just get it started. The next thing here I'm going to put is rate. Rate is a statement that tells Python, says don't do more than this number of loops per second. So if I have a 0.01, if I do a rate of 100, it'll be in real time. Okay, now I need to calculate the forces. So let's say Fs, I need the vector L. Ooh. Okay, let's put up here, I need a point. Let's see. What am I going to call it? P. Nah, let's call it point, I guess. What am I going to call the spring attachment point? Anchor? Yeah, that's fine. Anchor. That's kind of dumb, but it'll be. Let's just make it a point in space. Not even draw it. So it's just a vector, and it's at the surface of the moon or the spacecraft of the asteroid. So it's going to be vector RA00. Yeah. So now I can find L as the vector from the spacecraft to that point. So L equals spacecraft.pos minus anchor.pos. So it's going to start off at 1, see, because the spacecraft is 1 meter away, and that's it plus RA plus 1, and this is just RA, so it's going to be at 1 meter. Now L0 is 3, so that's going to give L, I think that'll work. No, then this should be 2.6. Then I'll have a stretch of 1.6. Okay, that's good. Yeah, and that is a vector though. So now I can say Fs equals negative k times magnitude of L minus L0 times norm L. So in Python, mag L is a built-in function that will return the magnitude of a function. Norm L is a built-in function that will return the unit vector for L. So I think that's it. Oh, and then I need to say if mag L greater than L0, then Fs equals vector 0, 0, 0. And there is a difference between the vector 0, 0, 0 and 0, right? 0 is a scalar. So this means that if it's, once it's past its compression, it won't pull anymore. Okay, now I need to calculate the gravitational force. So with that, I need R equals the craft.pos minus Bennu. I think it's got 2 ends. I don't remember. So that's R. Now I can calculate the gravitational force Fg equals negative G times Bennu.m times spacecraft times spacecraft, not scapecraft, spacecraft dot m times r hat norm r divided by r magnitude squared, mag r star star 2. So squared in Python, raised to the exponent is asterisk asterisk. Okay, so now I have my f net is equal to fg plus fs. Now don't think, oh well, they're in different directions, so one of them has to be minus. These are vectors, right? So I'm adding up the vectors. One of them may have a negative x component, but that doesn't matter. Okay, that first step was a lot. That's fine. So now we're going to do our next, we've calculated the force. Next is to update the momentum. Spacecraft dot p equals spacecraft dot p plus f net times dt. This looks weird, okay, because I have spacecraft.p on both sides of the equation, but this is not an algebraic equation. This is a make equal to equation. This is take the spacecraft momentum, add F net times delta T to it, and then make that the new momentum. So this updates momentum, which is really nice because then I don't have to worry about P1, P2, P3. I just worry about P. Next is to update the position. Okay, I did it. Okay. So the position is going to be spacecraft.pos equals spacecraft.pos. And this is spacecraft.pos is spacecraft is RS, right? That's the position of the spacecraft. Plus spacecraft.p times dt divided by spacecraft.m. And so I did it this order because if you did spacecraft.p divided by spacecraft.m times dt, the question is, what about the order of operations? This way it's unambiguous, even though I think it would work. And then I need to update time, t equals t plus dt. And that's it. Let's see what happens if it even runs. Error. Cannot subtract a vector, and so this spacecraft.pos, anchor.pos. I just need anchor. Anchor is okay. Anchor is not an object, it was just a vector. I made that mistake on purpose. It launched. You see that? It went up. Let's run this for 100 seconds, and let's run it faster. Oh, it's still going. It's not going very far because it's a big scale. So I did speed up the time. Let's do that. Yeah, check that out. Launching spacecraft. That's pretty cool, huh? I think it's working. Okay, I want to go ahead and change that time interval like I said I was going to do. So let's say that if R, I'm going to go down here. If the magnitude of R is greater than, if it's greater than 100. If it's greater than 100, then dt equals 0.1. So it's going to go 10 times as fast. We'll see what happens there. It will run faster too. Something happened. Okay. Mag of a function. Aha. So I said this, but I didn't calculate R yet, so I need to actually put it right down here. Okay, and let's run this for even 200 seconds because I don't think it's 100 meters up yet. Okay, and so it's going really fast up here because I've changed the time step, but I didn't change the rate. So I think I'm pretty happy. I want to now look at, because one of the things we want to see is what is very far away. So in order to answer that question, I need to make a graph. So if I graph the velocity as a function of time or distance, let's plot velocity as a function of time. Okay, so I'm going to say t graph equals graph, x title equals time in seconds, and then y title equals r in meters. No, I'm sorry, v in meters per second. Remember, I want the final velocity to be 12 meters per second. And then I can go over here and say f1 equals g curve, color equals color.blue. I like blue the best, I don't know why. So down here, I can plot f1.plot t and the velocity, which is going to be the magnitude of the momentum spacecraft.p divided by m. That's the velocity. So let's just plot that and see what happens. Aha, error. M is not defined. Oh, spacecraft.m. Okay, so you see it increases in speed very rapidly, and then it decreases in speed, and we get down here to we're pretty far away. So let's just run this for a really long time. Let's say for 700 seconds. Yeah, I think I picked a poor problem, because you'll notice here that it starts off with a very high velocity, but the mass of the spacecraft is so low, it just takes a long time. I need to run this a lot longer. 17, let's just go all out here. I'm going to change the time step too. Okay, I'm going to do that. While that's working on this, let's say if mag r is greater than 1,000, then dt equals 1. Check that out. Okay. There we go. Oh. What the heck happened? Oh, I see. So if mag r, I don't want mag r greater than 100. That means it's always greater than 100. So the radius, if mag r is greater than 100 plus ra, let's get rid of this and just see what happens. Yeah, because see, so what happens is I said it was always 0.1. There, that's better. Oh, it's still already at 12. I guess it's just really far away. Is really far away. So I mean, it doesn't have to be far away at all in order to be. Let's do it for just 100 seconds. I mean, it doesn't look like that's slowing down that much, although it is, I assume. Okay. Well, I think it's working. I think it doesn't have to. The mass of the spacecraft is so small, of the asteroid is so small, it does not have to be far away, and to get a appreciable change in speed. How about for fun? Let's do something fun. Let's increase the mass of the asteroid to 14. Let's just see what happens. It increases by a factor of 100. There we go. Okay, so it is working, right? It's just that my asteroid is so tiny. I'm going to use this new value because it looks a little bit better. And let's say, let's increase it even more, 15. There. Okay, cool. I like that. Okay, so now we can say, well, how far away does it have to get in order to be at a constant speed? So now I'm going to increase this time to 1,000 seconds. Oh, it didn't get far enough away. Check that out. It came back. Okay, that's cool. Let's put that at 14 and then run it. So it didn't have enough velocity to escape. So, but in this case it does, right? Because it's going to keep on going. And you can see the final velocity here is somewhere around 11. So I'm gonna show you how to solve this problem with momentum principle, which I've just done, but I didn't show you how to solve for the spring constant. Let me show the brute force way. So I would say I want it to be with a final velocity of 12. Well, I'm going to need, and I changed the mass, remember? So now I'm just going to change the spring constant. Let's just increase the spring constant to 5.25 times 10 to the fifth, and let's see what happens. Okay, it started off much faster, right? That was actually too fast. So let's go down to 2 times 10 to the fifth. Now you can see it's, again, slowing down. I want to get down to a final speed of 12. And you think, oh, this is so silly. You can't do it this way, right? You can't just willy-nilly change the values and rerun it. That's just barbaric. It's not barbaric, okay? This is called
doing it the way that you understand, and that's good. Okay, this one looks good. This is getting down far, getting closer to 12, but still too high. So let's do 1.5. I like that one. Look, pretty close. We're pretty close right there. Wow. But you'll notice how the velocity stops decreasing, right? It's far enough away that it's not even really decreasing anymore. And that's not even the whole graph. Look, so there's the whole graph. And so the final, that's 12. I did it. I guessed. Okay, so there's two more calculations I need to make. The first one is, and I'm going to make these as separate videos. The first one is, how can I do this without guessing the spring constant, rerunning it? And so in order to do that, I'm going to build a function. And I'm going to rerun this as a function. The second one is to see what happens if the mass of the asteroid is much smaller, so it's comparable to the mass of the spacecraft. And then I'll make that a separate video. So I got a couple more videos to come up, and I'm going to end, and I'll talk to you guys later.